So let's take a look at 5 card poker and some things that result from trying to count the number of possibilities for different hands. So 5 card poker hands, not worrying about the rules of the game, just the hands at the end of whatever process it takes to get to 5 cards. The best hand is a royal flush. That's an ace, king, queen, jack, 10, all the same suit. And so since there are 4 suits, there are 4 royal flushes. So that's easy to count. The values are selected ahead of time, they're determined, and the suits, we have one of 4 possibilities. So 4 royal flushes. Next best card hand is a straight flush. A straight flush is 5 cards in order, and they're all the same suit, but it's not a royal flush. So we don't have ace, king, queen, jack, 10, or if we're counting up, the low card is not a 10. So we want to count the straight flushes. And so to count the straight flushes, we can do this in a 2-step process. We can select the value of the low card, and then we can select the suit of all 5 cards. So the suit has to be the same, and the only distinguishing factor is the low card itself. So once you know the low card, you know the rest of the cards if it's going to be a straight flush. So to select the low card can be ace, which plays the role of 1 in that case. 2, 3, 4, 5, 6, 7, 8, or 9. It can't be a 10 because if we got to a 10 as the low card, then we would have a royal flush. And we've already counted the royal flushes, and we don't want to count those again. Once we've selected the low card, there are 4 different suits. We select the suit, so 4 choose 1 ways to do that. And so in all, we have 9 choose 1 times 4 choose 1, which is 36 ways to form a straight flush. The 36 ways does not include any of the 4 royal flushes. We've made sure we left those out of our counting procedure. We could count the straight flushes in a different way. We could count all of them, including the royal flushes, and then remove the ones that we had already counted. So in this way, we will again select the low card, but this time there are 10 choose 1 ways to select the low card because it can go all the way to 10. 4 choose 1 ways to select the suit, and so in all, 10 choose 1 times 4 choose 1 ways to form a straight flush. But that includes the 4 royal flushes, so we subtract those 4 from the 40, we get the same answer, 36 straight flushes that are not royal flushes. So let's look at the next hand, or at least another type of hand, and this is 4 of a kind. So 4 of a kind means 4 cards of the same value, then plus 1 more card, because we always have 5 cards in the poker hand that we're talking about. And so again, we want to write down in words the way of the process that we're going to go through, and then convert that into mathematics to do the calculation. So we can select the value of the 4, take all 4 cards of that value, then select the value and suit of the 5th card. So if we do this, we want to select the value. There are 13 choose 1 ways to select the value. That corresponds to the values whether we're thinking of ace as a 1 or ace as the high card. There are a total of 13 different values. So we're just going to select one of those. Then we're going to select all 4 cards of that value. So there are 4 cards there. We're going to choose 4 of them. There's one way to do that. We want to select the value of the 5th card. The 5th card has to be something different than the first card. We've already taken all of those out of the deck. And so there are 12 choose 1 ways to do that. And then the last part is to select the suit of the fifth card. There are 4 suits. We're going to select one of them. And so what we have, 13 choose 1, times 4 choose 4, times 12 choose 1, times 4 choose 1, 624 ways to form 4 of a kind. And so notice that the 4 of a kind is considerably more likely than, say, the straight flush. The number of ways to create 4 of a kind is 624. We could do that in a different way as well. So we could select the value of the 4 cards, take all 4 cards of that value, then select the 5th card without worrying about what its value or what its suit was. And so if we do it this way, from this approach, again, we select the value, 13 choose 1 ways to do that, take all 4 cards of that value. Now those 4 cards are out of the deck. If there were 52 cards in the deck at the beginning, as there are, we've taken 4 of them out. That means there are 48 cards left, and we select one of those. And so again, we get the same answer. We just got there by thinking through the process in a different way. Rather than focusing on the value than the suit, we just said, hey, there are 48 cards, pick one of them. So again, 624 ways to form 4 of a kind. There are several kinds of values, hand values that are possible. We're going to take a look at a straight. A straight is 5 cards in numerical order, but they're not all the same suit. So again, a straight can start ace as a 1, or the ace can be high. And in any case, for a straight itself, the cards cannot all be the same suit. If they were all the same suit, then they're straight flush. If they're the same suit with ace high, then that's a royal flush. We've already counted those, and we want to make sure that when we call something a straight, that we're not calling those other two, we're not counting those other two. This is a kind of narrowing it down to be more precise in terms of what kind of value are we looking at. So we want to count these, and we want to make sure that in our final answer we don't include the straight flushes and the royal flushes in those. We know there are 40 of those combined. We don't want our answer to include that value. Okay, so let's take a look at a couple of different methods for doing this and compare and contrast those to see what happens. So method 1 says, okay, we want to say in words what we're going to do. So let's select the suit of the low card. There are 4 choose 1 ways to do that. Let's select the value of the low card. The low card can be ace. It can go all the way up to 10. So there are 10 choose 1 ways to select the value of the low card. Then we have 4 other cards to select. Now those other 4 cards to select, once we have selected the low value and we know that we're talking about a straight, the values are already determined. So what we need to do is make sure that just at least one of the suits is different from the other suits. So we have the suit of the low card, we have the value of the low card. The value of the low card determines the value of all 5 cards. And all we need to make sure of is that of those remaining 4 cards, at least one of them is different from the others, or different from the first card that we've already selected, the low card itself. And so we can say, okay, well, how might we do this? We might think of this as, say, 3 of those cards we get 4 choices for, but that last card, or maybe not the last one, but one of the 4, we only get 3 choices for. It has to be different than the others. So if we think about it like this, then we say, okay, well, that would mean there would be 4 choose 1 ways to select a suit, 10 choose 1 ways to select the value, and then we select the suits of the other 4 cards. And so this would show 7,680 different hands that are straights without having all four be the same. Okay, so method one, following this procedure, would say 7,680 different straights. Let's take a look at this from a different perspective. We can, again, select the value of the low card. 10 choose one ways to select the value of the low card. We could select a suit for each of the 5 cards. Don't worry about whether they're all the same or not. Just select a suit. So 4 choose one ways for each of 5 cards means 4 choose 1 raised to the 5th power ways to select suits. So this would mean 10 choose 1 times 4 choose 1 raised to the 5th, 10,240 straights. But those straights include 36 straight flushes and 4 royal flushes in that total. And so from this approach, we're not worrying about preventing the suits from being the same. We just say, okay, we know we're going to pick up some situations where all the suits are the same in this 10,240. But in that 10,240, 36 straight flushes and 4 royal flushes, let's just subtract those. And that would reveal 10,200 straights. Well, 10,200 is not the same as 7,680. So there has to be a mistake somewhere. Method one, the procedure that we described, sounded perfectly fine. Go back, take a look at it. It is perfectly reasonable, the description that we gave of that process. Method two sounds perfectly fine, perfectly acceptable procedure. We overaccount, but we know we're overcounting. We're not worrying about the duplication. And at the end, we say, okay, let's just remove the duplicates. But they're not the same answer. And since they gave different answers, at least one of them is incorrect, and possibly both are incorrect. So when we know there's an error somewhere, sometimes it's a little bit easier to locate. But as we've seen before, when there's an error, when we know there's an error, sometimes when we look back and we find an error, we think, oh, we have found the error, we're done. But we do need to be careful, because remember, both of these methods could be giving a wrong answer. Both of them can be mistaken in some way. They both cannot be correct, we know that for sure, but we don't know that either of them is actually correct. So if method one is correct, then that means that method two is overcounting, that we haven't taken away enough things. If method two is correct, that means that method one is undercounting, that we haven't counted everything. And then again, they could both be incorrect, and we wouldn't know whether it's an overcount or an undercount. All right, so we want to analyze this. So let's go back to method one and take a look. It's hard to tell whether that answer is correct. So one thing that we often try to do is to solve a smaller, easier version of the problem that we can actually analyze. And so a smaller version of this, if we still keep the 5 cards, a smaller version is to reduce the number of suits. So we can't reduce the number of suits to 1, because then there's no problem there. There are no straights that aren't also straight flushes. But let's say there were only 2 possible suits. So matching what we said before, if that counting procedure was correct, that would mean that there are 2 choose 1 ways to select the suit of the low card. There are 10 choose 1 ways to choose that value. And then choose the suits of 3 of the other remaining cards, and then that would mean that the last suit had to be different, and so we only have one choice in that case. The first two steps, select the suit and then select the value, are certainly correct. So if there is an error, then it would have to be in counting the number of ways to select the suits. It would be in the portion of the problem that is in these last two numbers in our computation. So continuing or focusing on that aspect, we fixed the suit and the value of the low card. The other four values are determined, so we don't need to worry about their values. The only thing that cannot happen is that all four are of the same suit. And so we want to select this so that at least one of the five is different. For the two card or the two suit procedure, the formula suggests that we just wrote down suggests that there are 8 ways to do this. 2 choose 1 raised to the third times 1 choose 1. So that would be 8 ways if that procedure is valid. However, if we look at this, there are 4 cards, 2 suits to choose from. That means that there are 16 possible ways to select the suits. And of those 16 possible ways to select the suits, the only one that is not permitted is the one in which the 4 suits, or the suits of the 4 cards, are all the same, and they're all the same as the very first card. So that value is incorrect because it undercounts. The 8 undercounts the 15 possible ways there are to actually fill out those remaining 4 cards. So the idea here is that in method 1, that procedure that we wrote down for counting the number of ways to set the suits of those remaining 4 cards doesn't work when there are only 2 suits. It undercounts with 2 suits, and so since the procedure was the same with 4 suits, then we know it's undercounting with 4 suits as well. So when we take a look at this, the first parts of the calculation from method 1 are correct, but the last part is an undercount. So we're undercounting the overall number of straights. We want to try to fix the formula based on what we just saw. And so in terms of selecting the suits for the last 4 cards, rather than it being 4 choose 1 to the third times 3 choose 1, it's 4 choose 1 to the fourth minus 1. The only thing that's not allowed in selecting the suits is that one situation where we select the suits of the last 4 cards and they all happen to be the same, and they happen to be the same as the very first card. So in this calculation, this would mean that there are 4 choose 1 times 10 choose 1 ways to select the suit and value of the low card, and then 255 ways to select the suits for the last 4 cards, and that would correspond to 10,200 straights. All right, so we were able to revise method 1 based on what we saw with an easier version to correct our count, and it gave us 10,200, which corresponds to the answer from method 2. And we did that independently from method 2. We weren't trying to get the answer of method 2, but now we have 2 different ways of counting that both seem correct, and they both give the same answer, but we still would need to check further to see, did we make some other mistake that possibly happened in both cases and we didn't realize it, and that gave us the 10,200. Turns out that if we do that, everything is fine. Those the revised method 1 and method 2 have no additional errors, and the correct number of 4 of a kind is 10,200. And the reason that the word description of method 1 sounded fine is because the word description is fine. The problem was with that one part of the formula that we tried to use. It undercounts what we were trying to count, The words were fine. The maths part was an undercount. It was incorrect. All right, method two, that approach intentionally overcounts the number of straights, then subtracts away the things that we knew from the beginning shouldn't have been included, but they were easier to count and then just throw away at the end. The original version of method one tried to build up to the correct answer, but it undercounted in trying to build up. And the revised version of method two builds up at first, and then for that last portion, its method is to do an overcount and then take away the one thing that doesn't work. So it's a mixture of the two methods, of a straight overcount and then subtracting away things, or completely just building up. Method two's revised version, or method one's revised version, excuse me, does a partial buildup, and then for the last portion, it overcounts and then comes back down to get to the final answer. And so if you can find a way to revise method one or solve the problem that does not involve subtraction of things that are not wanted, then I'll give you bonus points for finding that. All right, so from this idea of doing an overcount and coming back, this gives us a method of sometimes overcounting and then undercounting and working our way to the answer that's called the principle of inclusion and exclusion, or shortened to PIE. So you all often see in texts or things about counting, you see references to pi. And unfortunately, it's just counting by overcounting and undercounting. So let's suppose in this red circle that this is set A, B is the blue circle, and C is the green circle. The little blue dots are the things that are in the different aspects, the different components of those sets. And in this case, we can just count the blue dots and know exactly how many are there, but we're going to illustrate a method that we will use in situations where it's not so easy to just count the blue dots. So what we want to know is we want to calculate how many things. So the bars are read cardinality of or size of the set. And the set that we want to count is A union B union C. So we want to know how many things there are total inside all these dots. So we're looking at counting the blue circles, the blue dots, but we want to do this in this more general way. Okay, so we want to know the cardinality or the size of the union. And so when we think about this, we could just count everything in terms of each individual set. So we're going to overcount, and then we're going to come back to fix the errors. So if we overcount, the overcount would say, let's get the size of A plus the size of B plus the size of C. And if we count the dots themselves, we know that there are 8 inside of each circle. So 8 inside the red circle, 8 inside the blue circle, and 8 inside the green circle. And so in that case, we know the answer is 15, and 8 plus 8 plus 8 is too big. But otherwise, we knew the answer would be too big, even if we didn't know how many there are, because we know there are some things that are in both sets, both A and B. And then there are some things that are in A, B, and C. So these blue dots that are in the overlap of the red and blue are counted as part of the red portion, and they're counted as part of the blue portion. Then this one dot in the middle is not only counted there, but it's counted again as part of the green portion. So with A, the cardinality of A plus the cardinality of B plus the cardinality of C, some of these dots are counted twice, and this one in the middle is counted 3 times. The ones out here that are just in one circle have been counted 1 time only, so they're okay. We counted them once, never going to count them again in terms of a duplication. Those are counted, they're part of the total, but these inside the middle portions have been counted too many times. So what can we do? We can say, well, these things in the overlaps have been counted too many times. Let's take those off. A intersect B, A intersect C, and B intersect C. Let's remove those. And so we counted them, these things here, we had counted twice. And so when you subtract that, these three, these two, and these two have been counted. They were counted twice, then we took away one, so now they were just counted one time in the total. But the reason this value is too small, this turns out to be 14, is because this one in the middle, we had counted 3 times, once with A, once with B, and once with C. But then we took them away when we subtracted A intersect B. So that one was reduced to being counted only one time. Then when we looked at A intersect C, we took it away again. So it was reduced to being counted one time, which would have been fine, but we went too far. We subtracted the intersection of B and C. So now this one point in the middle, this dot in the middle, has not been counted at all. And if there were more than one dot in the middle, then all of those would have been counted 0 times total. We overcounted, then we took things away, and we took away too many things. And so what we can do at that point is add back the intersection of all three. And so if we do that, and looking at all of the pieces, 8 plus 8 plus 8, that was the original number of things in each set. Each of the intersections, A intersect B and A intersect C, had 3 elements. B intersect C has 4. So 8 plus 8 plus 8, minus 3, minus 3, minus 3, and then add back that 1 point in the middle, and we have 15, which is the correct answer in this case. Now, what happens? We didn't need to do that again for this particular problem, but in other scenarios, this will be helpful because we will be able to know those smaller pieces of information. Or sometimes we know the bigger piece and it's one of the smaller pieces that we're looking for, and we can figure out or know the others, and then we can solve for that smaller portion that we're trying to find in that case. And so what happens? We have broken the problem down in a similar way that we have done in a couple of the other instances, intentionally overcount and then subtract things away. Well, in those poker hand scenarios, we could stop. We overcounted and then just subtracted once, and we subtracted exactly the things that we wanted. In this inclusion-exclusion procedure, sometimes we've gone too far. We overcount, and then when we subtract things away, we subtract away too many, and then we have to add those pieces back on. If we had more than 3 sets with our overcount, undercount, then maybe it goes into another overcount and then finally fixing it. So going back and forth with overcounts and undercounts. And that's why it's called inclusion-exclusion. You include some things, you've included too many, you exclude some things. Sometimes you exclude too many, so you have to include some other things. Back and forth with inclusion and exclusion until we get to the correct answer. And so again, there are lots of times where it's more difficult to count the actual answer. And in those situations, we want to use a method like this that is general and will allow us to figure out the pieces. And so we will look at some things that don't look like inclusion, exclusion would be able to apply, but we will be able to overcount and then undercount in an appropriate way until we narrow in and focus on the answer. All right, so as usual, if you have any questions, you can send me an email. You can ask on Discord, in the comments. Let me know what you're thinking about, and we will have plenty of practice for counting using these methods and other methods, some that are combination. Maybe it's a bad choice of words since combinations is a particular kind of counting. Maybe variants of the different pieces, or we're using multiple ideas in one problem to solve something, but that we break things down into their smallest pieces in order to be able to make sure that we're counting everything correctly. So we need to be able to say things in words, and then we need to be able to put it all together mathematically.